Okay, so good afternoon, everyone. I'm Tetsuya Ogata, so now I work at Waseda University and Japan. So today I'd like to share this type of the topics. So actually, thank you for the inviting me. It's very pleasure to give my idea to share and also share everyone here. So actually, the first I'd like to start this topics in deep learning and called AI recently. So actually, deep learning shows very good performance in many different types of application, image processing, sounds, and natural language processing. But as you all know, it still remains many problems in deep learning for application in a real system like a robot. So actually, I believe that we need to solve this problem to connect to the next generation of AI. So actually, the deep learning currently, of course, applies in many robots in a different way. And one is recognition. Of course, deep learning shows a very good performance in such a recognition path. So how to recognize object shapes and postures and positions for the manipulation. That is one way. And another promising and very, very well-known way is reinforcement learning. So robot actually, I try to through the trial and error, interact with the environment. And so actually, human designer gives some kind of a task. And so robot can train it could be estimate and expected rewards to complete the task. This kind of way is not agreed. So very natural way to apply these machine learning techniques for the robot systems. So I'd like to show another idea. So actually, one common sense is both ways of recognition or reinforcement learning is that now the designer try to robot acquire the kinds of optimal models for the mapping from the input to the output. So for the sensory input to the regular object condition, or from the action sensor conditions to the expected rewards, something like this. But I think that it is almost impossible to acquire the complete perfect models, even have the many trials, many training data. So because robot actually works in the real world, unpredictable world. So here is an idea that a robot or some system working in the real world requires to modify real time and adapt to the dynamic environment in the real times. So we recognize that even the deep learning we used, the robot can acquire the incomplete model. So I try to show some concept of deep predictive learning where the system predict and also at the same time modify correct the internal conditions to adapt such external world. So here is a kind of very cartoons to explain the idea of the predictive coding. It comes from cognitive science areas. And for example, here humans try to recognize this model, like an Earth, okay, Earth model. And so here actually acquires the sensory, real data. And this is the space for the perception. So we should recognize the sense and perception are not so completely the same. Okay? And here, he imagines the Earth should be this map. But actually it shows this map, okay? So you can see some prediction error between the real world and some internal models of actually his predictions. So how to solve these problems? Actually, there are three ways, I believe. So one way is that I'd like to start explained here. So changing the internal models. So that is sensory input, some result of the interaction with the world. So if there are some prediction error codes, so one way to solve this problem is change the internal models. That is learning. Very common sense machine learning people. But as you know, it's very high cost. But we can see there is another way. One way is to then change the prediction in the section these perception spaces. So we can recognize that we show the different direction. We see the different direction. So he can imagine another maps. So it can be rotated in mental spaces. So actually he generated this spaces, but it's imagined in the brain. So it's not real. But so by changing such a cognitive spaces, he can adapt to the decrease in prediction error. And another way is that actually changing the senses by the action. So because we have the body, we can interact with the world. So we can change the environment. We can change the out world. So this is one of the ways to minimize the prediction error. Okay, based on this concept, we showed some demonstration using real robot. Okay, this is one of the examples done at 2016, little bit old works. So here now, we collect some data. Actually, he now controls this robot for the operating robot to folding the towels. So, but actually, this is the data. But so in here, so after training, so the system always try to predict to the future motion at the same time, also try to predict the future images. So, but you can see this is a real one input, and this is a predicted images. But actually, this towels here is towels put in the desks, and this towels placed in the untrained positions. So this position is not included in this training data. So you can see the very, very unclear boundary between towels and table. That means now the system try to generate some images, some fake images. So he can generate the image to reduce such an error, to continue to complete the tasks. It's not real. That is very important. So prediction learning is of course, a way to try to predict future, but it's impossible to predict everything. So now we use this image to adjust to the environment. At the same time, so the robot to adjust the motion, slightly adjust the motion to predict, to reduce the prediction error. That means it could adapt to the changes of the environment. So this is one example. So maybe you can see the more clear movie here. And so the robot can adapt to the change of the environment like so. This is a towel places in an untrained position. And he changed the shapes and slightly. Of course, it's not trained. So, but the robot can adapt to this such a changes. Also, he can put an unknown towels. And so at the same time, the robot can put on this types and so book, of course, unknown object. So now he predicts the towels, fake image, towel image, but he can complete the task. So by adapting the environment to image, to change the perceptions in the world, then the robot can complete the task. This kind of real-time adaptation is very important. And it will be connected to the kind of the idea of feedback controls in the very preliminary levels. So this kind of dynamic adaptation is very important when we consider the real robot, working in the real world. And based on this idea, I many collaboration work with many different types of company, like Denso, Hitachi, or something like this. And so all these robots saw the folding, picking the salad and folding towels, and opening the door, and wearing the powder and different types of liquids, all works based on this predictive learning. So just human gives some experience data to the robot, and the robot is adapt to such an environment in a real time. And this is some recent works, and we released in May this year. So now robots, so from the pickings this zippered part. So from starting the picking, so then this handling condition is always changed, but the robot can adapt to the such a change and also can opening then work like this, zippers like this. This is real speed, and this is scenarios on how to collect the data. Actually, we trained the robot just 36 times with the different shapes. And this is another example for just picking the object. But sorry, this is another example to how to adapt the robots. So based on the experience and just opening zippers, you can see the robot dynamically to adapt to the change of the shape of the back. And this is another example. So the robot can imagine the future images. So it can ignore some other noises. So for example, this is a real image. And this is predicted images. And also that means it's a fake image. So he just focuses on this object and he ignores another object. That's a fake image, right? But by using these fake predictions, the robot can complete the task. And so another example is that handling an object for a cooking robot. So you can see the robot now interact with such this kinds of materials and select the tools and pouring the object like this. And so here the robotic has a tactile sensing and force sensors. So firstly, he's senses an object with an active sensing manner, not just using a visual image, but by touching and interacting with object, the robot can recognize even unknown object. And then he can select some suitable tools and also generate a suitable motion to the picking up or pouring. So I cannot explain the detail of these figures, but the base architecture is the same. So here is predictive parts. So you can see it try to predict the every sensing motion, sensing information, external sensing and internal sensing. So to reduce the prediction error, so then it can generate the motions. And this is a training experimental setup. We train these 6 targets and tested these unknown objects. And first, he used this tool. This robot used this tool for the active sensing. And after that, this robot selected these tools. Okay, then after the training, we can see the latent space in the neural networks and the recurrent neural networks. So you can see that we change some conditions of each such materials, and the robot seems to be succeed to recognize each object. Also, then you can see some boundaries. It could be used to the criteria to do which tool the robot should be selected. And at the same time, after training, the robot could recognize these unknown target like this. So here and again, I'd like to emphasize again, so is that these object is recognized not before us handling BS vision. The vision is actually very strong, but it's not enough. So, but after the handling or after the interacting with this object, then the the robot can recognize this object. Actually, we now check this success rate is even these phases. So actually, image, if you use only the image, so some of the object is very hard to recognize. So success rate is regulated like this. So by integrating some different types of sensors, tactile force sensors, then we keep this kind of success rate to complete the task. Yes, this is an example. So actually, the robot failed many times, so something like this. So then our analysis, so the robot requires many different types of sensor informations. Okay, so by using the less times, and I'd like to introduce our new project. We started last year called Moonshot, supported government, Japanese government, quite big project. Maybe you can easily find the name in the website. And our project proposed the project manager Shigeki Sugano, Awasa University. My PhD supervisor. And this project aimed to the robot which can support the human daily life in many different scenery, and called the AIREC. We call the AIREC, AI-driven robot for embrace and care. So we in this project we aim to the robot, we can support many different types of tasks. So I usually show these figures. So by comparison the smartphone, so smartphone actually compared to these dedicated devices, so each performance is of course these devices are better than the smartphone. But by combining these different types of function and into the one devices, it generates a new kind of value to the humans. So we can see now the robot developed in many different ways for the different tasks. But if we could develop the one robot, so it can be partially realize each task. It could show the very new and very impressive for our daily lives. And here we consider co-evolution between the robots and AI. So maybe here many people already know that the robot itself can generate a very intellectual behaviors by using one body. So especially by using a soft and flexible body, the very intellectual behaviors emerged with many complex softwares. But at the same time, I believe that we could enhance this kind of function by using our predictive learning framework. By influence of each other to the robot hardware to the enables new types of AI, the deep learning models, and also our models to enable to improve the hardware path. Repeating this process, we could lead to some novel robot design. And here I'd like to show the very preliminary experiments currently we done. So this robot had quite big powers. Actually, it can support this very big, heavy object, and each joint has a torque sensor and impedance control. So very easy to adapt to the environmental changes. So actually, this motion, we do not use learning models. Just depends on such impedance control. But you can see robot is moving very smoothly and complete these types of tasks. And so project is organized like this. So to develop the new types of hardware parts and AI parts, and find new types of applications. So for daily life support, oil care or medical care, something like this. Also, we prepare some other group to get the feedback from the require social research with collaborating research, social research collaborations. Okay, that's all my talk. Thank you very much.